So as much as a wire with current creating a magnetic field will therefore give a charge in the vicinity of that wire going at a velocity v, it turned out that it, of course, had a force on it. But you can also have a situation where you have, for example, two moving charges. So let's say this example, okay? Two positive charges move side by side in the same direction at constant velocity. The charge in each is 3 microcoulombs. The velocity is the arrow points in the direction of the velocity. The magnitude is 6 times 10 to the 7 meters per second. The question is, what is the magnitude and direction of the magnetic force on the top charge due to the bottom charge when they are shown in this configuration? The magnetic force, okay, not the electromagnetic force, the magnetic force. All right, so go. Give it a shot. Step 1. Calculate the magnetic field generated, okay, by the bottom charge. What would be the magnetic field created by this charge at this point where you have the other charge? Okay, another hint. All right. If you have this charge at the origin, the unit vector would be like so, right? So if this is 3 centimeters, and this is 4 centimeters, and this is where the other charge is, okay? This angle theta, okay? So our unit vector would be cosine theta I plus sine theta j, right? What is the vector velocity in this case for that bottom charge? V vector would be equal to V vector would be equal to
6 times 10 to the 7 meters per second.
To the 7 meters per second in the direction I.
Wait, that's actually 1/5 of the speed of light.
That is.
Wouldn't relativistic effects start playing into this?
You have to get. I mean, you would have to. Sure. But it's still at only a 10%. Because we're still about and then you have to square that, so it's still small. The effect is still very small. Yes. Both charges have the same charge, which is 3 microcoulombs. You're writing today? Good. Good. Let's see. No.
No, I'm finding the beat.
Yeah. Yeah. Okay, you're just writing now. You're just drawing now. This is rather slow. You're just writing now. You're studying. Nothing. Oh dear. All right. Well, sorry. We have a bunch of things to cover, so I had my bike ride, so I'm all like full of energy. You're still working on your caffeine. All right. So, all right. So I told you what is R, right? Unit vector R. The distance is in centimeters, so it's this squared times this squared, and it's squared, so we have that. Mu 0 over 4 pi is 10 to the minus 7, and charge is the charge of the particle that's traveling, the one that's here, right? So that is B in the direction. The first component of the cross product is 0, the second is I cross J, which gives us K, right? Does that make sense? So imagine you have a current, right? A positive charge is this way. You use your right hand corkscrew rule, and indeed, the magnetic field should be pointing out of the board. So the fact that we got K makes sense. All right, what is the sign of the angle? Well, it is 4 over, it's a 4-3-5 triangle, right? So it's 4/5, and therefore the magnitude of the magnetic field is 5.76 times 10 to the minus 3 Tesla in the K direction. So now what is the force on this charge? Well, it's the charge, or its velocity, which is also going in the X direction, plus the magnetic field, which is going in the K direction. All right? So, indeed, this gives me this number, which is about 1 Newton in the negative J direction. Let's see if that is the case. So we know that for if it's moving in this direction, right, the force on a charge Q will be equal to QB cross B, right? So the velocity of the particle is like that. The B magnitude is going out of the board, so the force with my thumb is going down, so indeed the force must be going in the J direction. All right, go over this problem at home carefully. This is a typical thing that we either it's a quiz or an exam problem, okay?
Wait, is there a quiz today?
Yes.
Mm.
So, all right, so you have another challenge. What would be the opposite? The force on the bottom charge to the top charge. You can ask yourself and try to do that
It
one.
would be wait, if they have the same charge, it would be
Yes.
the same force,
The
but that's in the
same
opposite direction.
magnitude, exactly, but the net force on it is going up.
Mm-hmm.
Okay. All right, so now we go to the next topic, which is Ampere's law. All right. So, how to use Biot-Savart law to calculate? We already covered this. No, we can now calculate magnetic fields produced by moving charges or a current carrying wire. Right. Now, we will use Ampere's law to calculate the magnetic field from symmetric current distributions. Okay. Something about these current distributions will allow us to do something neat mathematically to calculate magnetic field without using Biot-Savart's law, which, as you remember, we have to calculate integrals, and some of you might not be too happy about that. But it's good to do it. It's good to do it. But so this is another way to do it. It's called Ampere's law, and it's sort of reminiscent of the idea of Gauss. All right? Gauss's law. All right? So, okay, Ampere notice the following. If we take an infinite wire with a current I, and we are at a distance r away from the wire, the magnetic field has the same value, right? So if you are at a distance r from that wire, and you just go a distance r anywhere, the magnetic field is exactly the same value, right? Mu 0 I over 2 pi r, right? Where r is a distance away from the wire. If we now integrate B over the circumference of the circle of radius I, meaning we do a path integral of B dot dl, where dl is a vector that goes on that circumference, all right? B and dl are parallel to each other, right? You take up the circle and the B is always tangential, and dl is always tangential to the circle, and they're traveling on the same direction. So B dot dl is just B dl. The magnitude of B is mu 0 I over 2 pi r, and dl is just a segment of that circumference, and we talked about that being r delta d theta. So if I everything is a constant. You see that the arc cancels out. I get mu 0 I over 2 pi d theta, but when I integrate over the circle, I get a 2 pi. So the net result is just mu 0 times I, which is independent of the radius. Very much like Gauss's law, right? We end up finding that the charge enclosed by a surface, it doesn't matter the surface, the shape of the surface is the size of the surface, meaning it's independent of the radius or how big it is. It just cares what was enclosed by this. In that case of Gauss, the surface. In the case of Ampere's law is I create this path, all right, closed path. It's important that it's a closed path. All right, this closed path creates like a imaginary surface that is bound by this. Imagine a shopping bag. A shopping bag or a bag has a rim, okay, and it has a surface. You can take any shape, like if I blow bubbles, you know, when you're a kid, you put it in soap. The membrane can be just completely flat on the ring, or I can blow through it and I can deform it. Mathematically, they're the same thing. But here, what you basically are saying is, if I have this rim, I'm asking how much current is going through that surface that is generated by this rim. And the total current going through that rim, the area crossing the area defined by this rim is simply mu 0 times I. All right, so let's see if we chose that to be perfectly circular, radius r, but what if my path is somewhat arbitrary? So I'm going to make it arbitrary, but in a way that mathematically it's simple to do. So half of the wire, the path is a small circle, the other half is a big circle, and they're connected by these vertical lines, right? These vertical paths. So if I integrate this E dot dl over this closed loop that now is not a circle, but sort of funny looking, all right? It's simply the integral from, let's say that I start at A to B, so I'm going counterclockwise. Why? Because the current is going towards U, and the magnetic field should be going in circles around the wire this way. So I'm going to go from A to B this way, so dl is parallel to B, all right, in this case. In this case, from B to C, I'm going to go perpendicular to B, right? B, dl is coming down, B is going that way, so they're perpendicular to each other, and therefore this term is 0. Then I'm going to go from, where is it? B to C, then from C to D goes through the little circle. Again, I'm going parallel to B along the circle of radius R1, so I'm leaving it like that, and from D to A, again, the dl and B are perpendicular to each other, so they cancel out. So I'm left with these two terms, which is the magnitude of B out meaning the magnitude of the magnetic field traced by the larger radius, plus a term where the magnetic field corresponds to the magnitude of the magnetic field at a smaller radius. All right, for the part that is out, its magnitude is mu 0 I over 2 pi r out, and for the one that's in, it's the same expression, but r in. Now the dl for the outer surface is r out d theta, and for the one for the inner circle is r in d theta. So when I put everything together, you will see that I integrate this one from A to B corresponds to an angle of 0 to pi, and for the C to D term, this one, the angle goes from pi to 2 pi. And so I end up adding these two terms, okay, which gives me again a 2 pi, which cancels this 2 pi, and again I get mu 0 over I. So I took an arbitrary shape, convenient of course, but I got this result. So I get to the general result, okay, that B dl over a closed path will be equal to mu 0 I, the current enclosed by that path, all right? You can think of it as also the current that goes through the area that is, so I choose a rim, like so, right? And inside this rim there's an area, and you can think of this current going through it, right? Like that. So it crosses it. Now, what happens if I choose a path that doesn't include the current? So let's go back to that integral that we had. All right, I go from A to B, it's 0 because B and DL are perpendicular. Then I go from C to D as also 0 because the path is perpendicular to B. Then I have the path from B to C, okay, and the path from D to A. In the path, again, the current is going out of the board and the magnetic field is going counterclockwise, all right? So when I go from B to C, my DL is going against the magnetic field, right? The magnetic field is coming this way, my DL, I'm going from B to C, I'm going this way. So I'm going counterclockwise. The magnetic field is going counterclockwise while I am going clockwise. In this case, from D to A, my path and B are going parallel to one another. So, for the out one, since B is parallel to DL, I get mu 0 I over 2 because I only do half the circumference, right? From pi to 2 pi. But since DL and B are 90 degrees from each other, I basically end up with a negative sign in front of the integral. And therefore, a minus mu 0 I over 2, again, only half the circumference, that's where the half comes from. And therefore, when I add these two terms, I get 0. Indeed, as it suggests, the integral of the closed path integral of B dot dl, the path integral of the magnetic field on a closed path, all right, is 0 if no currents are enclosed. All right, so that's the general term. It's sort of like Gauss, right? It's the same concept. All right. Now, of course, if we have several currents, all right, again, you would indeed have this expression where now I enclosed corresponds to all the enclosed currents. Some of them could be going up, some of them could be going down. You add them, all right? Add them. In this case, the current 2 would be negative, right? And therefore, that would be my total current enclosed. And if the path integral is easy to calculate, I can get B, the magnetic field.
So DL is never perpendicular to magnetic field, like at some angle?
It can be at any angle. Like the previous slide, we had situations where the DL was perpendicular to B, and areas where B and DL are parallel to each other. In fact, of course, you can always break down DL in terms that are perpendicular and parallel, right? So only that is parallel contributes to this contour integral. Any path that is perpendicular to the magnetic field does not contribute to the path integral. All right, so question for you guys. The figure shows, in cross-section, of course, okay, you're seeing currents coming in and out of the board, all right, perpendicular to the plane of the figure. If the currents I1, I2, and I3 all have the same magnitude, for which path, or bless you, if there are many, or maybe only one, are the line integral of the magnetic field equal to 0? I'm going to give you 30 seconds. Think about A. Is the path integral in this case 0? For A, what is the current enclosed by A?
0.
0. Exactly. What about B? Is that 0?
No.
No, it encloses a current. What about C?
0.
0. So A and C are 0 up to now. Okay. What about D? Is it 0 or not 0?
No,
Not
it's
0.
It's not 0. Right? You have 2 coming out, 1 going in, so it's not 0. So what are the only ones that have 0? B, right?
Yeah.
A and C. Okay? Question. A cylindrical conductor with radius r carries a current I. The current is uniformly distributed, okay, over the cross-sectional area of the conductor. Find the magnetic field as a function of radius, okay, to the axis of the conductor. Alright. So now first, let's take a path. So it's any arc from the center all the way out. Let's start with a radius, a path integral, okay? That is consistent with the wire, right? The wire is length infinitely long, so the magnetic field comes this way, right? It curls around the wire. And even if the wire is thick, inside the wire it probably has magnetic field going like this as well, right? It doesn't suddenly go this way, it just goes swirling around, like that. So let's first take the path, all right? The outer path, the one that encloses the big path, that already the current is, all the wire is enclosed by. So what would be the magnetic field for R greater than the radius of the wire? If the radius of the wire is R. Well, Gauss's law states, Ampere's law states that the closed path integral of B dot dl must be equal to mu zero enclosed current. The total enclosed current for R greater than R is the whole wire, the whole current. Okay, so I enclosed will be the whole current I. Now B dot dl is again, as long as your radius R is always the same and greater than R, we can integrate B dot dl, right? So the integral of B dot dl in this case is simply B 2 pi R. Again, R is greater than the radius. So now we put these two things together, and therefore B becomes mu 0 I over 2 pi R, which is what we knew already, right? For a while. Okay, again, R is greater than R, right? We follow the same formula? Yes?
Why does 2 pi R move to the denominator?
Because I want B.
Oh, okay.
I want the magnitude of the magnetic field, right? Now, for R less than R,
Yeah, I think that's
what is the charge enclosed? The charge enclosed by my loop, if my loop is smaller than the wire itself, right? The thickness of I cannot enclose a whole I, right? Now the current is uniformly distributed. That means that the current density would be simply I over the area, which is pi R squared, right? That's the current density. So the current enclosed would be the integral from 0 to R, where R is less than the radius, R, of J, okay, D, area, right? The area is J, and it's 2 pi R dr. That would be the area from 0 to R, and that would be R squared over 2. So of course, not surprising, it's J pi R squared, right? So if the area enclosed by the inner loop is just pi R squared, where R is smaller than A, times the current density will give me the total charge enclosed, which is what? Which is just simply I R squared over R squared, right? Where it's a proportionality of the areas, right? A ratio of the areas. That gives me the total current enclosed. What about B dot dl? Actually, the expression is exactly the same, except that now R is less than R. So what is B? B would be equal to 1 over 2 pi R, right? Times the charge mu 0 times the current enclosed, which is I R squared over R squared. 1 of the R cancels out, and I get I mu 0 I over 2 pi R over R squared. So it has a linear dependence on the radius. So here are the results. For R less than R, we have R, it's linear, okay? It's 0 at the center of the conductor, It increases linearly inside the conductor, and then it decreases as 1 over R outside the conductor. The wire carrying a current, okay? And that's how you apply it. Let's look at in the last 2 minutes. All right, one last problem. All right? Imagine, sorry?
Wait, what is J unit?
The current density.
Okay.
The current density. Now, using the same concept, try this one. A solid conductor with radius A is supported by an insulating disk. Okay, so let's say that it's floating in air, okay? On the axis of the conducting tube with inner radius B, okay? So there's something insulating in here, and there's a hollow conductor, okay, which is carrying a current in this direction. All right? And the inner one is carrying a current in this direction. The currents are distributed uniformly. Okay, so that means that you can simply describe the current density as the current divided by the area, the cross-sectional area of the wire, right? Derive an expression for the magnetic field at points less than the radius A, between A and B, okay, between B and C in this region, and outside of R. I'm just going to do 2 and you do the rest at home. All right? This is Ampere's law. For A, did we already solve that problem?
Yes.
Yes, because I only care for enclosed currents. So if my path is smaller than the wire radius, we already got it from the previous problem, right? So B R less than A has to be equal to mu 0, okay, I over 2 pi A squared R, right? That's what we got from the previous problem. That is for the radius less than A. Now in between A and B. Now it's a path where there's nothing here, okay, and it covers this one, the inner one. What should be the magnetic field expression in that region? What is the total charge, total current enclosed? In that case, what is the total current enclosed? I, exactly. So B is equal to mu 0 over 2 pi R times I. Right? What about, now this is the one that's tricky. I'm going to skip that and you try this one. I'll give you a hint. 4. What if my path is all the way out for a radius greater than C? What is the total current enclosed?
I.
0. Because they're going in opposite directions.
Oh.
And they're the same magnitude.
Oh,
Okay?
and that's like a coax cable.
Yes, of course. It is a coordinate. So this is A, this is B. For R less than B greater than A. Alright? C, I'll give you a hint. B is equal to 0. What is the hint? What is J? What is the current density for this case? What is the current density for this case? The net area, so you have to do pi C squared minus pi B squared is the total area of cross-section. Divide that amount by I, right? I. And of course, they're going in the opposite direction, so it has a minus sign, right? All right, try it at home. Time for the quiz. Who wants to help me?